Hi guys, Rick here, back at it with another video. So it's for digital and Boolean algebra, digital electronics and Boolean algebra. So I'm using a simulator, a game to simulate to test my outputs and inputs. It's Prison Architect. It's just playing at the background. So for digital electronics, there are usually 7 gates. I'm not sure if there are others. There might be others, but depending on what I've seen so far, I've seen 7. So there's an AND, an OR, an NOR, a NOT, an XOR, and an XNOR. So for an AND, this is the truth table. For AND, it means both inputs. I'm using 2 inputs. All inputs should be high for you to get a high. So for 0 0, it's a 0. For 0 1, it's a 0. For 1 0, it's a 0. For 1 1, it's a 1. And is slightly stingy. You need all the inputs for you to get a high. For an AND, it's the opposite. It's getting the outputs of an and then putting a NOT in front of it. So for 0 0, it will be high. For 0 1, it will be high. For 1 0, it will be high. For 1 1, you should get a 1, but it's not in, so it's a 0. For OR, either of the inputs or if either of the inputs is high, you'll get a high. So for 0 0, it's 0. 0 1, it's 1. 1 0, it's 1. 1 1, it's 1. And for NOR, it's for AB, the inputs are AB. It's 0 0. It's the opposite. Neither of the inputs are high, so you should get a low, but it's the NOR of an OR. So it's 1 0 1 0 1 0 0 1 1 0. And then there's a NOT. NOT is just it does the opposite of the input. So if the input is low, you get a high, and if the input is high, you get a low. I'm using zeros for lows and ones for highs. Remember, these are switches. It's just a switch. So at this state, it's at 0, and when it's connected, it's at 1. I hope you have seen that. And then the other gate is an XOR. XOR, one of the inputs needs to be high for you to get a high, and if both of the inputs are the same, you get a low. So for 0 0, they're the same, you get a low. 0 1, they're not the same, you get a 1. 1 0, they're not the same, you get a 1. 1 1, they're the same, you get a 0. XNOR, it's the opposite of this. So for the same inputs, you get a high, and for the different inputs, you get a low. Sorry for that. Then I was trying to come up with a derivation of an SR, the 2 XOR. So you come when the inputs are high 1 and 1, it freezes the previous memory. So and when the inputs are either when it's 1 0, it starts from the bottom, or it starts from the top going down. It goes off, and then on, off, and then on. And when the input is switched, when it's 0 1, it starts from the bottom, off, then on, off, then on. So, and then from there, when it's at off, it flips, it goes to on. It's the opposite of the input. So when you get when you get a 1 0 and then you try to remember the memory state, you need to time it at when it's halfway. So when it's 0, it will remember either of the bit. It remembers the 0 and 1, and when it's at it's at 1 0, when it's at 0 1, when it starts from the bottom going up, you can freeze the memory. So you freeze it, it's at now, it remembers the previous state. So from there, so you get there are two gates, two XORs. So the inputs, so it's A and B. The inputs are S and SB, R, A and R. So for SB, it means the output of B, and then since it's for the S, it becomes SB. And for the outputs of A, it's RA, and then it's R. So for S and SB, it's 0 0. I'm taking possible possible inputs and then doing the comparison, the math, the Boolean computing, and then giving you the outcomes. So for this, the first one, S and SB, it's 0 0 0 0 1 0 1 0. You get 0 0 1 1. This is the XOR truth table. So 0 0, it's the same, you get a 0. 0 0, it's the same, you get a 0. 1 0, it's different, you get a 1. 1 0, it's 1. So these are it's for Q. Now and then this Q is being fed back to R. So it's R and then Q. For RA now is Q. So it's the R and S, they have been fed. I'm feeding them the same signal. So it's the same. This one is the same as this one. So 0 0 1 1. Then coming to the ones for R, it's 0 0 0 0, and then the outputs are for Q. So it's 0 0 1 1. You get an output of, for 0 0 it's 0, 0 0 it's the same 0, 1 1 it's the same 0, 1 1 it's the same 0. So these outputs are the same as the original inputs. So when you come to cycle, for this set of outputs it's 1, for this set of outputs it's 2, and then this is the same as this, so it's 1. So you get 2 states, 1 cycle. This I'm trying to derive. Okay, let's continue. And then from there, you come the other sets of inputs. It's 0 0 0 1 1 0 1 1. So I'm counting from 0 1 2 3. It's normal counting. So for 0 0 it's the same 0, 0 1 it's different 1, 1 0 it's different 1, 1 1 it's the same 0. So and then from there, so these are the first sets of outputs, and then for these sets of outputs are being fed back to, from the S you get the Q, and then they're being fed back to the R. Then from there you get R. They are the same inputs are the same as S, and then you feed them the outputs of Q. I mean, this now will be Q, Q. So R, and then the outputs of Q, it's 0 0 0 1 1 1 1 0. So Q bar will be 0 1 0 1 0 0 the same, 0 0 1 different high, 1 1 the same, 0 1 0 different high. So you feed this input, these outputs are the same as this one, so the cycle is the same, 1 2, and then back again to 1. So, and then train them for, okay, we now go again to different sets of inputs, 0 0 1 0 0 0 1 0. These are it's the same as this one here, but the number of states are the same as this one. These states are 4, these states are 2, so it's 0 0 is the same, 0 0 is one, another it's the same as this first state, 1 0 is, and 1 0 is the same state. So 0 0 0 0 is the same state, 1 0 1 0 is the same state. For 0 0 it's the same, 0 1 0 1 0 0 0 1 0 1. These outputs are being fed back to R. They are the Q, so it's R and Q. You get what you can't repeat. 0 0 1 1 0 0 1 1. So 0 0 it's the same, 0 1 1 is the same, 0 0 0 it's the same, 0 1 1 is the same, 0. These outputs are the same as this one, so cycle 0, cycle 1, cycle 0. 2 states, 1 cycle. And then for now the opposite of this is just the same as this. It's the same inputs, and then now for SB we now imagine they are all highs. So it's 0 1 0 1 different 1 1 1 1 is the same, 0 1 1 the same, 0. These outputs are being fed back to R, which 0 0 I mean 0 1 0 1 1 0 1 0. You get a 1 1 1 when you get a 1 1 1 1, which is the same as the inputs. So first cycle, second cycle, I mean first state, second state, one cycle. You try the same as here. The inputs now it's oscillating from 0 1 0 1. This is 0 0 1 1. So 0 1 0 1, and then 0 1 1 1 0 1 1 1. Different high, same low, different high, same low. R, and then R is the same as this, so inputs are Q, 0 1 1 0 0 1 1 0. You get highs. Now, coming to this, I was trying to derive them using the kmap. So this For kmap, let me show you how a kmap works. These inputs are not for this one. So using a kmap, when you have a truth table of, when you have your outcomes, I mean the inputs, and then this will be output. So when the outputs are highs, you take those combinations of inputs. You get? So like here for 0, 0, 0, the output will be low. For 0, 0, 0, 1, the output will be high. And then always remember this rule, 2 power n. So these inputs are 4. So it's 2 power 4 equals 16. There will be 16 number of inputs, outcome, possible inputs. So like you have numbered them from 0, 0, 1 to 16, to 15 I mean. So there is a high at when position 3, which is 0, 0, 1, 1, which there's a high. There's another high at position 5, which is 0, 1. A is 0, A is, it's A bar, B, C bar, D. And then there's another here for it's A, B bar, C bar, D. And then for 13, it's A, B, C bar, D. Now coming to make kmaps. Kmaps are drawn like this. You divide the numbering according to 2 power n. So 2 power 1 is 2. So for this it's 2. If there are 5 of them, like A, B, C, D, and E, it will be A, B, and then C, D, and E. So this will be 4, and then this will be 8. They will go up to 8 of them, 8 possible positions. Hope you have gotten it. So like here, it can even be the another input can be A, and then B, C, D, E. It will depend on the spacing you have. If you are numbering, if you have a lot of solutions to solve, and you want them to go like this, you can have for A, so it will be 0, 1. A it's 1, so it's 2 power 1, it's 2. There will be 2 outcomes, and then these are 4. 2 power n, 2 power 4, it will be 16. So you'll have 16 slots going this way. Hope you have gotten it. Depending on your spacing, you can either number it like this: A, B, C, D, and then low key. So it will be 16 slots going down, 2 slots going this way. And then from there, I was trying, when you have these 16 of them, your kmap will be 16. So this is a structured numbering. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. You get? And then when you come to numbering them like this, it's 0, 0, it's position 1, 0, 1, position, 0, 0, position 0, 0, 1, position 1, 1, 0, position 2, 1, 1, position 3. And then same for this, position 0, position 1, position 2, position 3. You just get accustomed to now counting them like this. And then from there, you put your ones are stored here. So for 3 it's here, 5 it's here, 9 it's here, and 13 it's here. Let's me finish up, I eat and then smoke up. From there, when you're numbering of them, so I've shown you for 3, 5, 9, and 13. So you group them. Kmaps are good for grouping. The original solution, it's for you to come and say for position 3, it's A bar, B bar, C, D. Position 5, so it's A or A bar, B, C bar, D, or position 9, A, B bar, C bar, D, or A, B, C bar, D. Okay, so you see these are five outcomes. So for you to, and then when you start solving them, you solve them using Boolean algebra. I'll do this in another video. But if you want to just get a shortcut from this, you come to your kmap. You come and say for position 1, it's for this position, it's this numbering and this position. You get 1 1 0 0. For this position, it's 0 1. It's at 0 1 and 0 1. Position 1, position 1. This one is at position 1, position 2. This one is at position 1, position 3. So it's okay. And then the other technique for kmap, when you come to grouping them, you group them again to 2 power n. So like this one, it's alone. You group this here. This will be alone, so you write it down like this. So it's A, B, C bar, D bar. A, B, C bar, D bar. Or this one here, there are 2 of them, so you have grouped them together. So 2 power 1 is 2. 2 power 0 is 1. So you can have groups of 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, and then 20, 48. And then from there you have started it again. It's like 2. So from 20, 48, it's 40, 96. You get, it's 2, 4. And then from 40, 96 is 80, 81, 96, 90 something, 90, 92, and then 16 something. You get, if you have kmaps that big, either way, so these are 2's. So when you read this, you read it from this line 0 1, and this here, it's at this position 1 and position 2. So you read them 0 1 and 1 0, but now these are the same. Since they are conflicting, the 0 and 1 is conflicting and the 0 and 1 is conflicting, you put them as x. They don't care. It doesn't really matter which state it is. For any of the 2 states, it will just show you a high for the 2 slots. Hope you've gotten it. You can either group it again, this as alone, and then you group these 2 together. So you get a for position 0 1, for position 1 and position 1. So it will be 0, it will be A bar, B, C bar, D, and then for this will be, oh, I've shown you for this. And then for this it will be, since they are grouped together, it will be A bar, B, and then this one and this one are the same. The C is the same, so it will be, let me write here, A bar, B, and then C is the same. C will be high, and then the D is an X. Since it's high here, low here. So it's a don't care. Hope you have gotten it, but I've grouped it like this. So reading this is A bar, B, and then these 2's are conflicting, X and X. The other form, I'll show you the other form of overcoming this position of getting these X's, because when you have your solution is running away, you will come to find it later. And then for here, you get now this one. For the last one, it's position 1, A bar, B, and then this is at position 3, it's high. It's higher, it's C, D. So when you use this technique, instead of getting 4, I've gotten 3. You've gotten it, and it can even be simpler. If this position and this position are the same, the square will have gone like this. You group them like this. If this position, if it's here, you group them like this. grouping them from this position and this position, this position and this position, it's still groupable because it's this and then this, and then you get 0 0 0 0 and then a 1 1 1 1. It will be a bar, b bar, c bar, d bar, or a b c d. This outcome is for when it's here and it's here. So, but you see they are conflicting. When you come to solving them, your solution will be x, 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 x. But don't follow this. When you are coming now to making a circuit, make sure you represent it like this. So you come and draw, you put an AND gate, you have A, B, C, and D. And then, so these are lines. And then you come for position A, you note it here, feed it here. Position B, and then let me put dots to show where they're starting. You note it here, so it's a B note, and then note it, C note, and note it, D note. And then for the other one is A, B, C, and D. You come and put it here. So coming for the circuit of this, and then since the table is telling you, the equation is telling you this position and this position needs to be high, so you come again and put an AND gate. Don't put an OR, because the equation is telling you to OR it. Because if you put an OR gate here, this condition needs to be true. So AND gate, all of them needs to be the same for you to get high. You remember that. All of them need to be high for you to get a high. And for here, all of them, you're not in them, so you get a high here. This will be a not, an AND. For you to get lows, this will be lows. So 0 0 0, you note it here. It needs to be an AND, and then this is a 1 1, and then another AND 1 1. You get your output. If you put an or if you put don't cares any of the lines, you'll still get your solution, but something is getting lost. When it comes to solve it, use don't cares. But when it comes to making a circuit, it's slightly advisable to do the long way. So from there, this is the structured way. The other way, when it comes to engineering, there's a method called gray code numbering. So the numbering is like this, going down, going up, going like this, going like this, and then the outer box is going like this, and then this is going like this, number is going like this. These are for 4. If there were 8, like 0 1, you need to go 0 1 2 3. You put a mirror here, you number, you put a mirror, put another mirror here, so this mirror is covering all of this. So it's from 0 1 2 3, you go to 4 5, and then 6 7. This is going down, this is going up, and then this is going up, this is going down, this is going down, this is going, the numbering is going up, and then the whole of it is going down. So for you to get a simple way of, if maybe you're trying to feed them into a computer, you just start with the first 3 or 2 3 bits, like 0 0 0 0 0 1. Have I done this anywhere else? So let me show you with this one: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So from here you put a mirror. These sets of bits here are a replica of this. It's just that these have gone from lows to highs. You see, it's 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 1 1 1 1 0 1 1 1. You see, it's the same. You get. But if it was Greek code numbering, I would have gone this one, and then you switch, you flip. So if it was Greek code numbering, it would have gone like this for the first two, for the second, and then for this one, and then for this one, and then you put, you see, it's a mirror here, a mirror. This mirror covers these two, this mirror covers these four, so you replicate that 4. So I was going, you go, it doesn't change, it's down, up, and then down, and then down, and then up, and then you put another mirror, you go, you know, it's the same. So this mirror replicates this. That's for Greek code numbering, but for structured it's just like this. So let me show you why you might need to do both of the structured and the Greek code. So when you number Greek code like this, so it's 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. I've gone like this, like this, like this, like this, and then this one going like this. So the second set will go from this one, so it will be like this, like this, like this, like this. I hope you have gotten it. So now representing them, you remember it's for position 3. Position 3 is here, not here. So it's 0 1 2 3, and then position 5, it's 4 5. So there's a 1 here, there's a 1 here. Position 9 is 4 5 6 7 8 9, there's a 1 here. And position 13, so 9 10 11 12 13, and there's a 1 here. So when you come to grouping them, there will be this one, and this one. So your technique might change. You might just number them differently. You can just number them differently, or group them differently, as you saw here. You group these two and this one separately, or you just do it structurally. So it's this grouped here. So it's 1 1 A B C bar D bar, A B C bar D bar, or this one here, this position 1 and position 1 and 2. But 1 and 2, C is conflicting. So C is 0 here, C is 1 here. So that's I don't care. And D, it's the same. It's high high. So when you group them, you say A bar B X, they don't care, and then D. And then this one you group it separately. So it's